Okay, so let us get started. So, last time we were discussing the polynomial hierarchy. Okay. So, I will get into the discussion in a few minutes, but before that I just want to digress a little bit and talk about something else. So, we talked about space bounded complexity classes, okay, and we saw the class P space. Okay. So, let us look at a complete problem for P space. I will not prove the completeness part in our lecture, but I will motivate as to why it is a complete problem, and if you are interested in the proof you can always go back and read it, it is there in your text. Okay. So, we have seen what a Boolean formula is and what does it mean to say that a Boolean formula is satisfiable, right. So, suppose if we have a Boolean formula phi, we say it is satisfiable if there exists an assignment to the variables of that formula, which makes the formula evaluate to true or 1, however way you want to think of it. So, suppose, so what we are saying is there exists an assignment to the variables. Suppose the formula has n variables, what I am saying is that each of those variables can take a value 0 or 1. So, instead of quantifying each variable with a existential quantifier, I can generalize this idea and talk about variables which are bounded by the universal quantifier. Okay. So, instead of saying that a variable can take any value between 0 and 1, I say that well the formula has to be true for all possible values that the variable can take. So, whether it is 0 or 1 I do not care, it has to evaluate to true. Okay. I mean a very simple example is, suppose if you look at the probably the most simplest formula, let us say just a single variable x 1. So, this formula, I mean if you think of this as a formula, this formula is always satisfiable, right, because if you set x 1 to 1, it gets evaluated to 1. But if I want this formula to be satisfiable for all possible values of x 1, then we see that phi is not satisfiable, because if I assign 0 to x 1, clearly it is not satisfiable. So, this is what is the distinction between these two ideas. So, let us try to encompass this idea into a formal definition. So, a quantified Boolean formula which in short we will denote as QBF, is of the form sum Q1 x1. So, we will assume that the formula is a formula in n variables, Q2 x2 so on till Qn xn, such that we have some formula phi on n variables where each Qi is either a existential quantifier or a universal quantifier. So, when do we say that this formula evaluates to true? If for the appropriate setting of the Qi's, for example, if q1 is an existential quantifier, then I allow x1 to take any value 0 or 1. Okay. For any setting of the value, I will consider the formula phi. If q2 is an universal quantifier, okay, so then I want this formula to be satisfiable for all possible values of x2, that is whether it is 0 or 1. Okay. So, this is what I mean by a quantified Boolean formula, and the language TQBF, okay, so T stands for true, is the set of all quantified Boolean formulas, let us call them psi, such that psi is a QBF that evaluates to, or I should not say evaluates, that is satisfiable. For an appropriate setting of the variables. Okay. Huh? Yeah, I mean quantifiers are already fixed, but depending on the quantifiers I am giving values to the variables. That is what I mean here, right. So, if it is a there exists, I mean if it is an existential quantifier, it can take any value, and if it is a universal quantifier, it should be true for all values. That is what I mean. Universal quantifier 0 1, they are all Boolean variables, right. So, we are looking at Boolean formulas. So, each xi can take values between 0 and 1, and we can also assume in addition that phi is a formula in 3CNF. So, it is a conjunctive normal formula with 3 literals per clause. So, that does not make a difference. Okay. So, is this language clear to everybody? Okay. So, clearly we can see that this is a generalization of the 3-sat language, because if I set all my quantifiers to existential quantifier, that will basically mean that this is nothing but just the language SAT. Okay. So, the theorem is that TQBF is P space complete. Okay. So, I will just discuss the containment part, that why is TQBF contained in P space. In other words, we need to give an algorithm. So, how do you give an algorithm for this language, a P space algorithm? Right. So, yeah, that is one way to look at it. Yeah. So, let us give a recursive algorithm, and you can also give an iterative algorithm, but probably that will be more difficult to construct, because it will be an exponential time algorithm. So, yeah, so let us give a recursive algorithm. So, let me call this algorithm A, okay, which takes some QBF formula phi, and then tries to answer yes or no depending on whether phi is satisfiable or not. So, if n is equal to 0, so that is if phi does not have any variables. Okay. So, we are also considering the special case when I mean a formula consists only of constants, zeros and ones. So, it is a and an or of constants, in which case it is easy to evaluate it. Okay. So, then just output the value of whatever value you get by evaluating phi. Okay, so, it is just constants. Else, that is if n is greater than 0. Okay. So, if n is greater than 0, then we know that it has at least one variable. So, there is a quantifier associated with that variable. If q1 is an existential quantifier, what we do is we check the following two formulas. That is, we check the formula phi with x1 set, I mean x1 getting the value 0, so if a of psi with x1 set to 0 is equal to
simply return power of a x1 set to 0 and x1 set to 1. But in procedural syntax we have to just compute this.
but I mean what do you, yeah, we can just say that also, because this is just some value. So, if this is 1 or a phi x1 is equal to 1 is 1. So, either of these two return a 1, then we output 1. Okay. So, now we again go back to this if, else if q1 is a universal quantifier, then we check if a phi x1 is equal to 0 is 1 and a phi x1 is equal to 1 is also a 1. Okay. So, it is a very standard intuitive algorithm. Okay. So, the point is how much space does this take? So, the thing again is that space can be reused. So, when I am computing phi, okay, and I am making recursive call to phi with x1 set as 0 and phi with x1 set as 1, I can reuse the space in both these recursive calls. Okay. So, let us say that for a formula of size n and I am sorry, a formula with n variables and of size m. Okay. So, suppose phi has n variables psi and phi has size m, then the space taken with n comma m as parameters is the space required for n minus 1 comma m, okay, plus some constant times m, okay, because we need this much amount of space to basically write out this expression on the tape and then run the algorithm on it. Because basically what we are doing in this algorithm is that we need to write out what the the new formula would be on which I am running my recursive calls. So, for that I need some constant times m space. Huh? So, basically if you look at one iteration, how much space am I requiring here? Okay. So, to make a recursive call to A, this is the amount of space I am requiring, okay. And the same space can be reused here also. Okay. The only thing that I need to remember is what is the bit that this guy had output. Okay. So, that is the only thing that I need to remember. But then I need to, so to be able to run A on a particular formula, I need to know what that formula is, right. So, that is why I am just assuming that I write out that particular formula on the tape, and that requires some m space. Right, yeah. So, yeah, I guess you can make this some constant. So, yeah, so you have this thing globally written on your input tape, you can always refer to that, and probably you can replace this with some constant. So, yes, if you solve this, what you will get is something like order n times m, right. But what you are saying, so then you have to look at what the base case is. So, the base case is when you have 0 variables. So, s of 0 comma m will require some size m, right. So, what you are saying then will require n plus m, yeah, you are right. But yet does not quite matter because we have sufficient space. Yeah. So, yeah, so and yeah, the hardness part also can be shown again not with much difficulty. It is basically again looking at the configuration graph and then looking at adjacent configurations and coming up with a formula that encodes the definition of an edge between adjacent configuration. So, you write a formula which is 1 if there is an edge between two pair of configurations and which is 0 otherwise, and you appropriately encode it into a thing. So, I will not go into that part. So, let us come back to our discussion of polynomial hierarchy and let us see how this thing fits in. So, okay. So, what was the definition that we saw last time? So, it is the union over all I greater than or equal to 1 of the classes sigma I p. Okay. And what was the definition of sigma I p? Yeah. So, it is basically a generalization of the class N p, where instead of looking at just one, the existence of just one certificate, you look at alternative, I mean you look at in an alternating manner whether there exist different certificates with the universal and the existential quantifier. Okay, so, let us just write that definition down once more. So, L is in sigma I p if there exists a machine M and a polynomial Q such that for all strings x, x belongs to L if and only if there exist U1 such that for all U2 so on till some quantifier Qi Ui, the machine M with x comma U1 comma Ui evaluates to 1, okay, where all the UJs have length q of mod x, and qi is an existential or universal quantifier depending on whether I is odd or even. Okay, so this was the definition. Okay, and one of you asked last time that why do we look at alternating quantifiers, right? I mean, what if we have the same quantifier for two consecutive strings? So, can anyone answer that? Exactly. So, I mean, if we have two quantifier, I mean if we have two strings with the same quantifier, two consecutive strings, then basically we can just treat both those strings as just a single certificate with that particular quantifier. So, let us say if I had a there exists u1 and a there exists u2, I can think it of as the concatenation of u1 and u2 with the existential quantifier. Okay. So, what is the blow up? The blow up is only in the length of the string, okay. But then I mean we have that freedom, I mean then we can choose a polynomial q appropriately, okay, which is just twice the length of this polynomial. Okay. I mean we do not care what that polynomial is as long as it is a polynomial. So, a language is in this class if there is some machine and some polynomial. Okay. So, it is just that we will have a new q prime and a maybe a new machine which will deal with that, and the same thing happens if I have a consecutive universal quantifiers as well. And it is not only for two, I mean if I have any sequence of quantifiers which are the same, I can always club those strings together and put the quantifier preceding it. Okay. So, that is why always without loss of generality we can assume that the quantifiers alternate. Right. So, that changes the definition of the class. So, we will look at that. Okay. So, similar to sigma IP, okay, we define the class pi IP, okay, which is just a complement of sigma IP, that is it contains a set of all languages L such that L complement is in sigma IP. Okay. And now, I think that answers your question. So, if we look at the class pi IP, okay, we can also, I mean now since I have defined pi IP as the complement of sigma IP, I can state this as a theorem that a language will belong to pi IP if there is some polynomial time Turing machine M and a polynomial Q such that for all x, x will belong to the language if and only if for all u1 there exists u2 and basically again the quantifiers will all I mean they will alternate and there will be I such quantifications and the machine accepts the string with all those certificates. Okay. So, the difference is that what is the initial quantifier that I am starting off with. Okay. Yeah. So, yeah, so therefore, again we can define pi h also I mean the class ph also alternatively with respect to the classes pi IPs. So, it is the union over all i's of pi IP. Okay. and again these are very easy to see. Also, what can we say about the various sigma i's and the various pi i's? So, what can we say between, let us say two sigma i's, let us say you have a sigma I p and a sigma j p. Yeah, okay. So, for j greater than I, sigma I p is contained in sigma j p. Okay. So, this follows from the definition, okay, because if I have a higher j, I can just ignore all the additional strings. Okay. So, that we do not know. So, we know that there is a containment, but whether it contains any additional languages, that is something again that we do not know. So, again that is a good question, and people believe that all these containments are actually proper. So, people believe that within the polynomial hierarchy, so basically these are referred to as levels of the polynomial hierarchy. So, they believe that all these levels are actually different from each other, that there exist problems in each of these levels which are not contained in smaller levels, but that is something which is not known. Okay. Yes, yes. So, yeah, we will actually come to that. So, there are complete problems known for each of these levels, and actually that is not something very easy to see. I mean, I can just state that if you just look at a generalization of SAT again. So, what was SAT? SAT was right. I mean, basically SAT was I mean, you have certain variables and you look at I mean, does there exist values to those variables which makes it satisfiable. But instead of that, if you just generalize it, okay, so let me write it here. So, we can define the following language sigma I sat, okay. So, sigma I sat is the it is a set of all formulas phi such that there exists some vector u1 such that for all u2 and so on some quantifier qi with a vector ui such that the formula phi with all these vectors u1 through ui is satisfiable. Okay. So, I can treat the variables in this formula as some set of disjoint vectors where there exists some assignment to the variables in u1 such that for all possible values that can be assigned to the variables in u2 and so on all the way up to ui, this formula is satisfiable. And this is complete for sigma I sat, I am sorry, for sigma I p. Okay. I think this is actually an exercise in your textbook to prove why this is complete. So, this is again not difficult to show, but yeah. So, this is something which is kind of derived from the definition of sigma I p. I mean whether there exist other natural problems which exactly characterize these classes or not, that is something interesting. And I think up to the second level of the polynomial hierarchy, there are complete problems which are known. Okay. I mean there are other natural problems which are known to exactly characterize, for example, sigma 2p. So, sigma 1p is nothing but NP, right. For sigma 2p, I think there are known, but for sigma 3 and 4, you can come up with artificial definitions, but yeah, I mean I do not know what exactly what you want. Okay. So, yeah, so just coming back to this thing, what about let us say the relation between a sigma IP and a pi IP? What can we say about these two classes? Maybe for a different type. So, maybe let us say if we have some j. So, pi jp is co sigma jp, right.
So sigma I belongs to sigma pi jp if j is less than.
J is less than it is contained in this, yeah. So, in other words what we can write is for any actually I plus 1, I mean if I look at just pi I plus 1 p, so this contains sigma I p, okay. Because again what we can do is we can just forget the first quantifier, okay. So, we have some other still I quantifiers left which begin with the opposite quantification, okay. And in the same manner this is contained in sigma I plus 2 p. So, I am stating these theorems, but you guys should go and just work this out and convince yourselves, okay. So, they do follow from the definitions, but it is good to actually work them out. Okay. Yeah. So, the reason why I stated why I digressed and I talked about this p space complete problem is that, so now again we can see quite easily that for all I, okay, sigma I p is contained in p space. Yeah, so maybe I should not have erased that language, and the reason for that is if you look at the complete problem for sigma I p that I just actually erased out. So, that is nothing but a special case of the TQBF language, right. So, it is just a special case where we are only looking for some small set of variables, okay. And so, what we get as a corollary is that this entire class PH is also a subset of P space. So, there exists this entire plethora of classes and natural languages which sit between the class NP and P space, which makes a case as to why we study this hierarchy PI. So, okay, so let us look at another theorem that if P is equal to NP, then the polynomial hierarchy also collapses to P. Okay. This is what is referred to as the polynomial hierarchy collapses. Okay. So, again this is something that is not believed, because the hypothesis of this statement is not believed, but let us look at a proof of this. So, yeah, very difficult, but let us look at it. So, we will prove this by induction. So, what we will show is that for all I, sigma I p is contained in P. Okay. So, that will immediately imply that the polynomial hierarchy is contained in P. So, for I equal to 1, this follows from our hypothesis. So, if I is equal to 1, then sigma 1 p is by definition the class n p, which is equal to p by our hypothesis. So, therefore, the claim holds true. Okay. So, suppose it is true for I minus 1. Okay. So, how do we show it to be true for I? So, let L be a language which belongs to sigma I p. So, this means that there exists a polynomial time Turing machine M and a polynomial Q such that x belongs to L if and only if there exists a string u1 such that for all u2 some quantifier qi, ui and m on x1 x comma u1 up to ui evaluates to 1. Okay. And all the uj's belong to have size q of x. So, now we can define a language L prime based on this language. So, let us define L prime, which is the set of all tuples of the form x comma u1, okay, such that for all u2 there exists a u3 qy ui and m given x comma u1 comma ui evaluates to 1. Okay. So, I am just clubbing u1 together with the given instance x. So, now what can we say? What can we say about L prime? It has I minus 1 quantifier and it begins with a for all. So, therefore, L prime belongs to pi I minus 1 p. Okay. And since we had assumed earlier that sigma I p belongs to p, right. No. Here we have assumed that sigma I minus 1 is belongs to p. So, if sigma I minus 1 belongs to p, since p is closed under complement, pi I minus 1 also belongs to p, right. So, this also belongs to p since It's so that we still do not know, but what we can say is that since this is equal to P and P is, so this we know is closed under complement. Well, does not matter because P by definition is a subset of all these classes. So, we can write equal to also. Okay. So, if this belongs to P, that implies that there exists some deterministic polytime deterministic Turing machine M prime such that L prime is equal to L of M prime. So, now let us go back to the language L prime. So, when do we say that language, I mean an instance is L prime? So, by our definition, for all strings x, we know that x belongs to L if and only if there exists u1 such that M prime given x comma u1 is equal to 1. Okay. So, that is what our definition of L prime was, that there exists some u1 which together with the string x and for all these certificates x gave us 1. So, therefore, so if you just check this, so this is nothing but the definition of NP. So, therefore, L belongs to NP which is equal to P. So, so most of these theorems that you would see, I mean they will have this similar kind of flavor because it is just basically cutting down on the number of steps in the polynomial hierarchy and then being able to prove something. So, actually we can generalize this theorem a little bit. Okay. I will just state it as a corollary. So, instead of assuming that P is equal to NP, even if we assume something much weaker, that if okay, so for all I, if sigma I p is equal to pi I p, then what do you think we can say about pH? Okay. So, if I just fix some I, okay, so it can be for any I. So, basically do not confuse this for all I statement together with this. What this means is that if you fix any I that is greater than or equal to 1 and if for that particular I sigma I p is equal to pi I p, what do you think we can say about pH? Huh? Well, not quite. So, pH will not quite all the way collapse down to P, but it will collapse to sigma I of P. Okay. So, we have all these classes. So, let draw a small picture. So, we have the class P over here, okay, and we have the class NP and the class co-NP. So, P is of course a subset of these two classes. Okay. So, this is nothing but sigma 1 P and this is pi 1 P. So, where does sigma 2 P sit? So, sigma 2p again encompasses both these and it is something like this. So, this I have, you can think of this as sigma 2p and you have similarly pi 2p. Okay. And the hierarchy continues. So, each level of the hierarchy contains all the classes in its lower levels, okay. And each level of the hierarchy, I mean you can think that the sigma and the pi versions are in some sense separate. So, if for any particular level I, if the entire polynomial hierarchy above it, I mean if for any particular level I these two classes coincide, then basically what is happening is that the entire polynomial hierarchy that is sitting above it will collapse to that particular level. Okay. Yeah, it does not imply that even the lower classes would collapse, but at least we can say that the higher ones would collapse. So, yes, huh?
So it should be existential particular.
Which one? This one? No, it is not for one particular I, it is for any I. Right, no. So, that is why, so yeah, so maybe I can just rephrase the statement slightly differently. Okay. So, fix I, okay. Now, if sigma ip is equal to pi ip, then it collapses to that. Okay. So, this I that I am fixing can be anything. So, that is what I meant earlier.
That is equal to there.
No, but there exist again, I mean I do not know, I mean depends how you interpret it, but there exist would mean that for some particular I this is happening. It should be fine as long as you understand what is happening. So, that is what is important. But yeah. Okay. So, again this you can just try out as a proof. The proof is nothing, is just it is very similar along these lines where you have to prove it inductively. Just you have to start your induction from this particular I instead of from I is equal to 1. Okay, so I will stop here today.